Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from great scientist Albert Einstein, who says, "Great spirits have always encountered violent opposition from mediocre minds." That is true. A lot of us, we also face similar problems of being dragged down for doing some work. We need not worry about it. We should do the work to the best of our abilities. Let us recall now what we learnt in the last lecture. In the last lecture, we looked at various performance parameters, namely the various efficiencies like propulsive efficiency and thermal efficiency, overall efficiency. Although these efficiencies are not being very much used as a performance parameter in case of rocket engines, but it is profusely used in case of non-air breathing engines. But we have discussed so that we can find out where the losses are there, so that we can maximize the energy utilization. Today we will be discussing about the rocket nozzle, and for that we will be considering an ideal nozzle. A question might be coming to your mind, why you will consider the ideal nozzle? Because of fact that the processes involved in a actual rocket nozzle is quite complex in nature, because there will be some expansion which will be taking place, and there will be heat losses, there might be some chemical reaction which is still going on, the properties will be changing and other things. For example, like if you consider, this is your thrust chamber in this example, and this is a CD nozzle, and we can consider the propellant is entering in maybe in a kind of a liquid rocket engines or hybrid rocket engines. That is, we are considering as a station 1, and there will be a lot of chemical reactions which will be going on in this stress chamber, right, and there will be vaporization, and then in case of liquid rocket engines there might be regression of the propellants, and then this will be expanded in the nozzle. And this is at the inlet of the nozzle, because nozzle will be coming over here, CD nozzles, and this is your throat area. This is the throat, and most of the times in the rocket engine is called choked. The star we are using as a choked condition, and this E we are saying as a exit. The station is exit. And then of course the several assumptions we will have to make for this to analyze it, otherwise it will be very difficult to analyze in a simpler way. Assumption we will have to make, that is already we have discussed most of them, but I am just repeating. One is the quasi one dimensional steady inviscid adiabatic flow. What we are saying, the flow which is entering is a one dimensional, where it is leaving is a one dimensional flow kind of things what is having, right, but which is not true, because it is a diverging section of the nozzle. Therefore, the flow will be in the diverging. That means the flow will be having some R component. If I say this is your X component, this is your R, there will be theta component. So, all other components will be there, but here we are assuming only that along the axial direction the exit velocity and the inlet velocity will be there. And we are also assuming flow to be frozen. That means no chemical reaction is taking place in the nozzle, which may not be true all the cases. For all the cases it may not be true. So, ideal gas law we will be using it, and with a constant specific heat or constant thermodynamic properties, which is not true. Particularly the temperature across the station 2 to the station exit will be changing a lot, and so also the Cp value, the specific heat value will be changing, and there is no shock or expansion wave. However, expansion wave may be formed or a shock may be formed inside, or maybe oblique shock, maybe normal shock. All this can be formed depending on under what condition nozzle is operating. And the startup and the shutdown time is quite short in this case. That means we are considering that most of the times is operated so that the throat will be choked, and during the start and shutdown time the throat need not to be choked. And as I told earlier that it is the axially directed velocity at the inlet exit, and the flow is basically maybe 3 phase flow it may occur, but however we are considering is the homogeneous working fluid that will be prevailing in the nozzle here. And for these things we will be making all these assumptions to analyze the rocket nozzle. A question might be coming that what will be an error involved in that. You will be surprised to know that the error is not really much. The actual performance is something less than the 1 to 5% of the ideal one. So, therefore, one can really at least use this ideal nozzle analysis for design purposes without incurring much error. So, by if you want to analyze this thing, what we will have to do? We will have to consider the first the energy balance between the station 1 to 2. So, I can take a control volume here between station. This is your control volume for the thrust chamber between station 1 to 2, and we will also make some already assumption that is quasi one dimensional, that means, and also it is a steady, that means there is no component of the unsteadiness in this analysis. So, therefore, we can do a mass balance, that is mass balance is equal to m dot 1 is equal to m dot 2. That means, the mass is remaining constant across the station 1 and 2, and there is adiabatic process. So, that there is no heat loss is 0, the work, this is also an assumption, that is q dot is 0, and there is no shaft work. So, therefore, that will be 0, and change in potential energy is 0. That is the assumption what we will have to do, I think, not only for the thrust chamber, but also for the rocket nozzles. And now we are considering the first law of thermodynamics for a control volume systems in case of this thrust chamber between station 1 and 2, that is equal to basically total specific enthalpy at station 2 is equal to total specific enthalpy at station 1 here plus the delta SC. Keep in mind, this is the heat of combustion of the propellant. This is heat of combustion of propellant, and if we can assume the Cp is not changing between station 1 and 2, which is not true real sense, because there will be a lot of temperature increase will be there due to this heat release here. So, but however, we are assuming it for the simplicity sake. So, therefore, we will get that is total temperature at station 2 is equal to total temperature at the station 1 plus delta SC divided by Cp. So, let us look at in a TS diagram, that is you are at here station 1, and due to this heat release at a constant pressure the temperature will go up to here, and that is in the basically this process is taking place in the thrust chamber. So, now we will have to apply the first law of thermodynamics between station 2 and E, considering this is the your control volume of the for the CD nozzle, and keep in mind that this at the throat the Mach number is equal to 1, that is one thing. Of course, we may not consider that for our calculation, and in this case what we will be doing is that we will be applying the first law of thermodynamics for this control volume of CD nozzle, considering this is adiabatic, considering that it is a no shaft work, and also considering the change in potential energy. And with this we will know that total enthalpy, and there is total enthalpy at station 2 is equal to the total enthalpy at exit and per unit mass, because mass is remaining constant here, it is not changing, being a steady process. There is no heat release in the CD nozzle, as we are saying that is a frozen flow. So, therefore, the total enthalpy at the station 2 and station E is remaining constant per unit mass, and that we can write down ST2 minus STE is equal to 0, and then we can write down that ST2 minus STT is equal to Cp into TT2 minus TE, that is Cp is the specific heat and which is remaining constant. That this is happening in the expansion process from station 2 to station E. Keep in mind this is corresponding to the star. This is your throat area, throat nozzles throat area. We will be now using this equation and finding out basically the exit velocity expression. So, ST2 minus STT is equal to STT2 minus the HE plus VE square divided by 2. Keep in mind that this kinetic energy change is occurring in the nozzle of the rocket engines. So, and we are maybe we can assume very happily the velocity will be almost 0 at the exit of the thing, which may not be true, but we can assume that. And then we can express this in terms of temperature, that is Cp TT2 minus TE plus VE square divided by 2 is equal to 0. So, we can now get an expression for exit velocity, that is equal to root over 2 Cp TT2 minus TE. This we can write down is equal to 2 Cp, I can take Tt out here into 1 minus Te by Tt2. So, we can also use something isentropic relationship. We can now rewrite this thing as basically taking Tt2 out from this bracket, that is Tt2 1 minus Te by Tt2. So, keep in mind that we can use isentropic relation for Te by T2 and express this temperature in terms of pressure, because we are considering adiabatic and also no losses are there in the process. So, therefore, that becomes equal to root over 2 Cp Tt2 1 minus Pe by Pt2 power to the gamma minus 1 divided by gamma by using isentropic relationship. So, therefore, this Ve is equal to gamma Ru, and in place of Cp in this expression equation 10, what we are using for an isentropic relationship, gamma Ru divided by gamma minus 1 molecular weight. Basically, what we are using Cp is equal to Ru divided by gamma minus 1, this is molecular weight, and into this bracket 1 minus P by divided by P to power to the gamma minus 1 divided by gamma. Keep in mind that from this expression you can see that exit velocity from the nozzle is a function of not only the gamma, but also it is dependent on the temperature or the combustion temperature. It is dependent on the molecular weight and is dependent on the pressure ratio, that is PT2 by PE. And for a given combustion temperature, molecular weight must be lower to have a higher exit velocity. That means you have to choose the propellant in a proper way such that the molecular weight will be much lower, and that can be done by including some kind of lower molecular weight elements like hydrogen or chlorine or some other things, so that the product molecular weight will be much lower. And beside this, of course, you can also enhance the temperature by choosing the proper fuel and oxidizer ratio or proper propellant. Keep in mind that there will be a problem of not going for a higher temperature because of fact that higher temperature means that there is a chances that metal what will be using may be melted out, provided if the duration of the flight is higher, and it is also will be subjected to high pressure in the rocket nozzles, and also in the thrust chamber will be much higher. And beside this, there is another problem which will be coming. So, for the temperature there might be a dissociation of the chemical species. So, if you go for higher this thing, the temperature may come down. So, generally for a typical propellants 2800 to 3500 Kelvin can be used for different fuel air ratios. However, for when you use hydrogen and the fluorine, one can go for 5000 Kelvin without really much the problem of dissociation. And you can see that the pressure, the chamber pressure, this is your chamber pressure, should have a higher so that the engine size can be smaller, but as I told earlier, the higher the chamber pressure, then the problem of stress experienced by the thrust chamber and the rocket nozzle also will be higher. Therefore, we cannot go for a higher, much higher pressure also. So, let us look at the effect of gamma. If I take simply air gamma 1.4, the gamma divided by gamma minus 1 will be 3.5. That means, if I will go for another propellants which is will be different, like rocket exhaust, it will be around, let us say typical value is 1.2, then it will be gamma divided by gamma is 6, and whereas the gamma minus 1 divided by gamma is 0.167. If you look at this term, basically in this region, that means when the propellant is changing, the gamma is becoming a smaller one, then this will be higher value, that means this increases. However, this is having like this will be lower values. If it is a lower, that means this component will be higher. This component becomes, if this is gamma minus gamma will be lower values, this PE by PT2 will be basically higher values, so that this contribution will be lowered down. Of course, this will be increasing. So, keep in mind that this has to be a balance, and then one has to choose the proper one for to have a maximize the V, because this is having two opposite effects. And when you talk about this pressure, always keep in mind that if this is 0, this PE by PT2 is basically 0, you will get a maximum exit velocity, and that can be possible only when it is in the deep space or the PT2 is much higher as compared to the P. That is one way of doing. That means when you will be expanding the nozzle fully in the space where the atmospheric pressure will be 0, that means P is equal to P A, and the space in the space it will be 0. So, therefore, you can get the maximum. So, equation 11 becomes, right, V E max is equal to root over 2 gamma R U T 2 gamma minus 1 m dot, because this term will be basically, this term will be 0. So, in this case, so therefore, this equation comes over here, V is equal to 2 gamma R U T U divided by gamma minus 1 molecular weight. Keep in mind that in this case, when you change this gamma, there will be that means when you lower this gamma of the exhaust gas from the rocket engine by designing proper propellants, then you will find V is really is increasing very much higher. But whereas the V exit velocities, which you will not be really changing much with the change in the gamma as compared to the V E max. There will be some changes, but that changes is not much significant compared to the maximum exit velocity. So, that also we will be discussing little later on. We will see again this point. Let us now find out a relationship between the V E and V E max, and we have already seen expression for V E in equation 11 and V E max in the equation 12. Now, if you look at this is nothing but your this term, if I take this out, and this term is basically V E max. So, then I can by using equation 11 and equation 12, we can have an expression for V E divided by V E max ratio is nothing but root over 1 minus P E divided by P T 2 power to the gamma minus 1 divided by gamma. Keep in mind that this is a function of this pressure ratio and also gamma. So, therefore, we can plot this thing and see what we are getting, that B E divided by B E max is plotted with respect to P T 2 by P E, and you can see for gamma 1.2, this plot basically with the pressure is 0, I mean very small values, it is almost 0, and then it goes on increasing, and it in a very, when the pressure ratio between the pressure ratio may be something 2 to 25 kind of thing, there is a much variation between basically 2 to 20 kind of things. After that, it is asymptotically increasing. Therefore, generally people go for something for a better expansion beyond this 25 pressure ratios, and when it is going for gamma 1.3 and for higher, the V E V maximum is increases, right. So, therefore, one has to use this thing for higher pressure ratio, and keep in mind that these things has to be chosen, the pressure ratio across the nozzle, that means expansion ratio, the pressure ratio across the CD convergent divergent nozzle has to be chosen properly, and generally people go beyond something around this is P T 2 by P E is equal 25 to something 40 people use, but when you are expanding in the space or a kind of thing, when you are using the nozzle at the in the space applications, then and you are optimizing at the space, then one has to use for a high area ratio. People have gone even something around 70 to 100 kind of things, which is much higher. So, the area ratio accordingly area ratio also will be changing. So, we will see more detail about this rocket nozzles in the next lecture, and with this we will stop over. Thank you very much.